to the Crazy Hat Chemist. So another video here on thermochemistry, the second one. So let's get moving. Bam! Today we're talking about enthalpy, or delta H. Enthalpy, delta H. So here's an equation. We got delta H is equal to delta E plus the product of P delta V. I'm going to describe what each of these components here means, a little bit of verbiage here, and then details of it. So the change in enthalpy, that is delta H, is the total heat content of the system, which is the internal energy of the system plus the product of the pressure and volume change. Okay? So delta H is the change in enthalpy if we go back to that equation. Okay? Delta E is the change in the internal energy of the system. If there is constant pressure, the heat change, that is QP, is equal to the change in the enthalpy. If there is a constant volume, then the energy change of the system, that is QV, is equal to the change in enthalpy. So if it's constant for pressure or constant for volume, that term disappears effectively, that plus P delta V, and you have the change in enthalpy is equal to the change in the energy, the internal energy of the system. All right, so let me relate this to another equation here that you should be familiar with. Delta E is equal to delta H minus delta PV. Now, I'm hoping you're remembering way back into the gas unit and the ideal gas law. The ideal gas law is PV equals nRT. You see right there, there's the PV. So what I'm going to do is substitute in what PV is equal to. Okay, so now I have delta E is equal to delta H minus change, that's delta, nRT. Okay, so when the change in the number of moles of gas is 0, that is, there's no change in the number of moles of gas, then this product right here, the delta N, which is the moles of gas, is 0, and then therefore the delta E is equal to the delta H. That is, the internal energy of the system is equal to the enthalpy change. All right, hopefully you've got that. The change in enthalpy is a state function, and that is, it is path independent and only depends on the initial and the final states. Okay? Your bank account is a perfect example of a state function. It only depends on the initial and the final amount. Doesn't depend on how much you add. You could add a penny every day, or you could add $100 in one day to get to that $100. Okay? Another state function is you're traveling from home to school. So you could walk from home to school. You could take a bus from home and then walk a little bit to school. You could take a helicopter from home and then parachute down to school. Okay? It is path independent, just like the change in enthalpy, which is path independent. Okay? If the change in enthalpy is exothermic, then the energy is transferred from the system to the surroundings. The reaction gives off or liberates heat, and the temperature increases. The delta H is less than 0, i.e. the delta H, the enthalpy change, is negative, and the heat term for the enthalpy is always on the product side. Okay? If the change in enthalpy is endothermic, then the energy is transferred from the surroundings to the system. The reaction absorbs energy, and the temperature will decrease. The delta H, or the change in enthalpy, is greater than 0, i.e. the enthalpy change is positive. And the heat term for the enthalpy then, if it is endothermic, is always on the reactant side. Let's see how those two exo and endothermic processes are played out with a graph and an equation. Okay? So here is a graph of energy versus the reaction progress. A and B, separately independently, are two reactants, and C is the product. Now you should see that A and B are higher up than C. So A and B are higher in energy than C is. And this is characteristic of an exothermic reaction. The difference between A and B and C is the heat term. Okay, and here's an example of an equation. That is the combustion of hydrogen, that is hydrogen gas plus oxygen gas, produces water, and we have this plus 285. That plus 285 is on the product side. So when the products are lower in energy than the reactants, then heat is liberated, and the heat term is on the product side. Notice that if I were to just write the enthalpy change, that heat term needs to be a negative value, but when I write it in an equation, there's a plus sign in front of it, but it is indicated on the product side. Now this is counter to the opposite graph. The opposite graph is right here. A and B, the two reactants, are lower in energy than C, which is the product, and this is characteristic of an endothermic reaction. The graph is the same in that we have the energy versus the reaction progress. And the heat input is the difference between A, B, and the C. That is the reactants and the products, and that is the endothermic characteristic. Here's an example of that. We have 181 kilojoules plus 2 moles of mercury oxide, okay, giving you mercury and oxygen gas. This is a decomposition reaction. This is endothermic as noted with the 181 kilojoules on the reactant side. So it's an endothermic reaction with the heat term on the reactant side, exothermic reaction, heat term on the product side. Okay, exothermic liberates heat, endothermic absorbs heat. Okay, here is the system, and this is going back into physics, and hopefully you remember your physics. These are the surroundings. So the heat is released by a system when the Q is less than 0. That is an exothermic reaction. This is work that is done by the system, an exothermic reaction. When heat is absorbed by the system, that means that Q is greater than 0. Then work is done on the system itself. So hopefully that gives you a really good idea of enthalpy and the delta H and the change in enthalpy and a little bit of understanding graphically and where those numeric values belong. I am the Crazy Hat Chemist, and of course we have to have a crazy hat. And I got a crazy hat here to match actually with the color of my shirt. Thank you very much to some cheerleaders a long time ago who made me this hat. I greatly appreciate that. If you like that video, give me a thumbs up. Don't forget to subscribe to my YouTube channel. Find out more chemistry videos on my YouTube channel. And of course, I'd always encourage you, if you like these videos, then please donate to my website and you can get a cool sticker or maybe even a cool t-shirt. Check that out. Awesome. Have a fantastic day, and I'm going to see you next time. Bye for now.